Hello and welcome to this talk about data service automation for Cloud Foundry on Kubernetes. A few words about me. I'm Julian Fischer, CEO of a company called Anynines. We are building platforms for a living. We have history in Cloud Foundry, and we are now moving along with the community to explore Kubernetes. We've also been automating data services as part of our platform for years. So there's a set of data services based on BOSH automation, performing on-demand provisioning of dedicated service instances. So this is where a lot of the content of the talk is inspired by actual work that we are ongoingly do. So the data service automation topic is something that I've been speaking about for several years. So if you're familiar with prior talks, that's good. I'll try to explain basic concepts along the talk. If you think about data service automation in the context of Cloud Foundry, that's one thing. If you're thinking about Cloud Foundry that runs on top of Kubernetes, that is a different thing. So the context of this talk, to be clear, is we're looking into the automation of many different data services. So it's not about a particular database alone. I'm using Postgres examples excessively, but it's about, I think to this point, we alone have 8 or 10 different data services because customers are asking for different data services. So if you're a large corporate, it is very likely that data service automation is not a problem that restricts to a particular data service, but a set of data services. And it's interesting to see that a lot of existing data service solutions hyper-focus on one data service and one data service alone, missing the opportunity to share automation code among them. So on-demand provisioning of dedicated service instances is the next constraint we have in this talk, because you could also share a Postgres example by serving databases of a particular data service server, Postgres server, to various clients. Well, while this is possible to some degree, if you do that as at a massive scale, this won't scale very much. You'll run into issues such as noisy neighborhood and the like. So it is the leading paradigm of these days to provision databases on demand as dedicated resources. Could be a VM, could be a set of VM, could be a pod, could be a set of pods. Platforms, especially if they are a bit bigger, they tend to be global. That means you often have different infrastructures you serve. For example, Azure or AWS, Ali Cloud, or even on-premise infrastructure such as VMware or OpenStack. And therefore, a platform product and data service automation product should be able to work on all those infrastructures. As you can see with Cloud Foundry and Kubernetes, it is very likely that in your organization you want to use both. Some workloads are more suitable for running in a Kubernetes cluster, and other workloads will have an affinity towards Cloud Foundry. So whatever we build when it comes to data service automation should integrate with both. Large organizations, large platforms, they come with overhead, and therefore it is very likely that you will have thousands of data service instances. Otherwise, you don't have the economy of scale to make them economically viable. So we're looking at thousands of data service instances in the average case. Striving for full lifecycle automation is imperative if you're looking at scales like that, unless you have plenty of operators sitting around. As the lifecycle automation is not only meant for the platform operator, but also for the application developer who does not necessarily want to wait for a platform operator to provision a database. So I think in 2020, we are beyond this. On-demand self-service rules. So Cloud Foundry on BOSH, if you're running Cloud Foundry the traditional way, which is absolutely fine, then data service automation on BOSH is also fine. So you can still use that And even in certain cases, there's good reason to keep on using that. For example, the increased isolation level that virtual machines provide in contrast to pods. If you're using Cloud Foundry on Kubernetes, but you still have a BOSH with access to virtual machine orchestration, well, then nothing has changed for you either. So this talk basically focuses on the scenario where you have a pure Kubernetes environment, and for whatever reason you don't want to have a BOSH, and you'd like to lift or delegate the heavy lifting for data service automation to Kubernetes. So that's the scope. And as I said, there are already a few ifs to get to that particular context. So data service automation with Kubernetes, what's to be said about it? First of all, we are in a Cloud Foundry context. So I assume that there is a Cloud Foundry. And if there's a Cloud Foundry, then you want to have the CF create service experience, which ties to having a service broker that complies to the Open Service Broker API. So nothing has changed there. The Open Service Broker API, for those who are not familiar with it, postulates two different resources. A service instance is basically what your data service instance is going to represent. So if you're looking into Postgres, then a Postgres instance would be a specific Postgres that you can use as an application developer. In the Service Broker API, it's not specified whether this is a shared database from a shared Postgres cluster or whether this is a dedicated virtual machine or set of virtual machines. It's up to the implementation to decide what it actually is representing such a service instance. The other resource that often is used is service binding, which represents the corresponding concept in Cloud Foundry, the connection between an application and its service. So if you have an application that wants to access a Postgres, you'll create a service instance for Postgres, and then you'll bind your application in a service binding to that particular Postgres instance. So as I mentioned, the service broker design for on-demand service broker that will use BOSH for creating managed virtual machines is rather well known. So I'm using that as an example. If you're not familiar with that concept, I will try to introduce a bit. But you can also look into prior talks held at the Cloud Foundry summits. They will provide you with the necessary background. So in the context of BOSH, a service instance with on-demand provisioning of dedicated service instances, a service instance maps to a BOSH deployment, which in turn will create a virtual machine or a set of virtual machine representing the service instance. The service binding will create a username password will have to be stored somewhere. Let's say in your service broker, ideally in an encrypted way. So this is what service brokers are in the on-demand world with using BOSH. So in our case, we have a service broker that has dependency to our own Postgres. So it will store the state. For example, what are the service instances that have been created? What does my service catalog meta information look like? And what are the service bindings that exist? They will all be stored in the service broker's backing service. If you translate that, or if you migrate that concept into Kubernetes, how is it going to look like? That's the exciting question. And obviously, you won't orchestrate virtual machines, but pods instead. So instead of creating a virtual machine for a Postgres, you'll create a pod for Postgres. If your Postgres should be clustered, you'll create a set of pods. Which leads to the interesting question, how exactly are you doing that with using Kubernetes resources? And while there are several options you can possibly use, I think one of the more obvious choices would be to represent the service instance as a composite of different Kubernetes resources, including a headless service, stateful set, config maps, secrets, and jobs. So if we look into these concepts for a minute, the most important resource to understand is the stateful set. The stateful set usually comes with a headless service. In Kubernetes, there are several resources that you could use. You could directly create pods, but there are also replica sets and deployments, which are meant for application deployments mostly. And in recent versions, the concept of a stateful set has been introduced, particularly designed for data services. And they come with additional behavior. In some sense, a stateful set behaves like a replica set in the way that you can specify a number of replicas. If a pod is deleted, so you manually delete a pod of a stateful set or a replica set, the replica set or stateful set controller recognize that and recreate the pod. So that's nice. But in a closer relationship to a deployment, the stateful set also allows you to perform subsequent changes to a stateful set that will perform rolling upgrades, for example, a behavior that's unknown to replica sets but exclusive to deployments, otherwise excluding the stateful set. So the stateful set in this regard is similar to a deployment and therefore combines behavior of a replica set and a deployment without using them, by the way. A stateful set controller is creating pods. It also will create you a stable network identity if you use a headless service with it. And each pod in a stateful set has a stable identity. It has a number, starts with 0. So if you have 3 replicas, it's 1, 2, 3. The headless service will add a non-layer 4 load balancing. So usually services in Kubernetes perform layer 4 load balancing. The headless service doesn't do that. Instead, it creates DNS entries. So you'd be able to refer to a particular stateful set by using its headless service. It will resolve to the pod IP addresses that are behind that stateful set. So for example, 3 replicas, your DNS entry will respond with 3 entries with the IP addresses of the corresponding pods, and that will respond to changes rather quickly. So if a pod goes down and has to be recreated, the DNS entry will quickly resolve internally to your Kubernetes cluster to the new pod's IP address. Also interesting is that each of the pods with its particular number and its particular DNS entries also comes with a particular persistent volume. That's created through a persistent volume claim that's derived from a persistent volume claim template. So this allows you to be sure that a pod number 0, for example, could be the primary of your streaming replication in Postgres. When it comes back, it will come back with exact the same persistent volume. So if there's a deviation and there's an implicit role associated with that pod of the stateful set, for example, the primary, you can be assured that it will be the primary's disk being reattached in the event of a failure, which is very nice. Also, there's ordinality. So if you create the stateful set, these pods of the stateful set will be created in sequence, and they will be destroyed in the inverse sequence. So 2, 1, 0 during deletion and 0, 1, 2 during creation. Similar things apply to updates. Config maps are basically key value sets that you can use to store settings or simple configuration files. These config maps can be mounted or brought into pods as environment variables where you have to restart the pod in order to reflect upon changes of a config map. Or, interestingly, you can also mount them as volumes, which will turn the keys of the config map into files and if your process reads them repeatedly, they will also reflect upon changes of the config map. Secrets are basically also key value pairs meant for storing sensitive information. Interestingly, by default, they are not encrypted, but I think the main purpose of that is to let Kubernetes administrators plug in encryption for secrets. So it's wise to use them to store sensitive information. A job is a concept that allows you to create pods, number of pods, repeatedly execute them to perform certain tasks. You could, for example, run pSQL commands against your Postgres cluster if you want to. So all these are necessary and useful tools to have in the tool belt when performing or when doing data service automation with Kubernetes. So after the stateful set, we also, after having the service instances, well, which basically go down to creating stateful sets and satellite resources around it, it's interesting, how would you implement a service binding? And there is no equivalent of a service binding in Kubernetes. In conversations, people ask me often, but what about secrets? Are secrets close to service bindings? And I would say a secret is actually a set of credentials. So as a service binding also represents a set of credentials, then yes, they are similar. But where the difference is, if you create a service, a binding in Cloud Foundry, for example, for your Postgres, you expect a username, a database user, and a password to be created. And that, for example, is what the secret doesn't do for you. So a service binding will possibly use a secret to store the credentials and delegate the persistency to Kubernetes etcd, but it won't do the actual user creation for you. So you have to do that yourself. So you need a bit of logic to create that username and password. Which brings us to an interesting concept in Kubernetes, which is the Kubernetes CRD. A CRD allows you to specify a new data type that's owned by the Kubernetes API and stored in its etcd. So think of the Kubernetes objects that you can natively create. For example, a pod. You create a specification for a pod, you kubectl apply it, and then Kubernetes knows that you would like to have a pod with a particular name using a particular image. And you'll get a feedback from Kubernetes immediately that, yeah, that object is taken care of, but it doesn't tell you anything about whether this actually worked or not. Because it's a declarative system, and storing the information that you want to have a particular pod does not mean that the pod is already there, because there is a controller being responsible for taking care that this resource is created afterwards. So similar to that, a custom resource definition allows you to describe a particular new data type to Kubernetes, which the Kubernetes API will then take care of and also persist it for you in its etcd. Here's a simple example. This specification describes a custom resource definition that will teach Kubernetes how to store Postgres objects. So in this case, the object that we would like to specify has only two attributes, the number of replicas and the Postgres version. You can see that we specify the name. Here the kind is A89 PostgreSQL, or you could name it PostgreSQL. I think I'll do that in the next slide. You can also define short names for it. So for example, persistent volume claim is the regular name, and the short name is PVC. So you can do the same thing with CRDs. It's also possible to specify validation rules, but, well, dig into CRDs if you are interested. So the takeaway here is that once you apply this specification and you ask Kubernetes to list the API resources, is that there's a new entry showing up, providing you with a new resource kind, in this case A89's PostgreSQL. If you specify such an object, you can create then objects of this kind. In this slide, I renamed it to Postgres because it's easier to read. But despite of that, it complies to the same specification. So you can declare a Postgres version and the number of replicas for a Postgres database, for example. If you apply that, you'll create that object, Kubernetes API will take care of it and stores it, let's say, as a desired state. Yes, a Postgres is to be created, but it doesn't do anything else. So the custom resource definition can be imagined as a class in Java, and the objects you create are like the objects of the class in Java, but there's no behavior. In order to add behavior to that, you need a controller. So CRD controllers, here's an example, will have to take care that if you hand them over the specification of whatever the resource, it will dispatch that into the usual CRUD operations, creating a resource, updating the resource, and deleting it. For example, creating the Postgres instance, updating it, or deleting it, with all its different subtleties. For example, it could be an upgrade that changes the number of replicas, or it could be an upgrade that even changes the version, major or minor. So the controller will have to take care of all the complexity and dissecting this change in state in the specification and make sense of it by translating it back into changing resources of other kinds. So for example, changing the specification of the replica set. If your replicas go up from 1 to 3, well, you'd be updating the replicas in your stateful set. As you can imagine, the Postgres example here, if you have one node, well, that's fine. If you specify 3 nodes, that doesn't bring you a distributed database yet. You have to set up replication. You have to set up a replication user. So all these additional semantics will have to be covered in the controller, maybe not executed, but at least taken care of and delegated somewhere. So writing those controllers and defining custom resources seems to be a repetitive task if you're doing data service automation, and therefore tools emerged that will help you do that. The Operator SDK is one of them. Oversimplifying speaking, it helps you to describe CRDs and apply them to the cluster, and it will also allow you to create CRD controllers more easily. And it does that with a lot of Go code. To be fair, there's also support for Ansible and Helm support, but as a data service guy, I would say Helm and Ansible, it's not particularly what I'd expect here. So the mightiness of Go for describing the lifecycle of data service is a good thing, but you need to structure lifecycle events and the library that performs those things very, very wisely, unless you're ending up in a nightmare spaghetti code operator. So the Operator SDK comes with code generators for custom resource definitions and controllers. It'll postulate a reconcile loop that will basically give you 2 versions of the specification of an object, and then the controller has to take corrective measures. There are also other abstractions or other tools emerging to build operators. One example is Kudo, which is a generic operator, very opinionated. So while let's say the Operator SDK is more like Ruby Sinatra, then Kudo is more like Rails. It's not a particularly accurate comparison, but yeah, forgive me that. Kudo introduces a concept called workflows, where you can specify a sequence of resource changes. Because a lot in the lifecycle management of a data service will be around modifying the stateful set, changing the service, adding the config map, changing the config map, and so on. So it seems natural that having more control over that and be more descriptive about that sounds interesting. And well, you could first think that, wait, is a workflow imperative? But at some point, each declarative system has to do something. So there must be a converging algorithm to be executed. So a workflow description in data service automation is actually a good abstraction. The question here is, Kudo expressive enough, or does it get in your way? So maybe you try it yourself and form your own opinion. Another question is that the way it should be done? Because in data service automation, you also have different layers of abstraction where you need to take action. So it's not only about changing the stateful set alone in its specification, but taking the example of changing a Postgres from 1 replica to 3 also requires setting up a database user for replication, changing the configuration file, and maybe invoking commands such as pg base backup on only a few on the cluster nodes. So in this case, not on the primary, but on the secondaries. So this requires a bit more fine-grained control of what happens inside of the containers and pods. And there's no declarative workflow-like description in Kudo here. And this is not, maybe Kudo will do that at some point, but I just believe that there's room for improvement left. But try it out yourself, make your own opinion. So the picture, drawing the picture together, you have a Cloud Foundry that sits on top of Kubernetes. Then you'll have a cloud controller. This is where you register your service broker. So if you're familiar with service brokers, nothing has changed so far. The service broker will delegate, the cloud controller will delegate to the service broker. The service broker, in our case, delegates to a deployment component that will then, for example, write BOSH manifests. Now in Kubernetes, you could instead write Kubernetes manifests, for example, to create a stateful set, for example, to create config maps, and so on. And in order to bring that together more easily and more consistently, especially if you're also targeting Kubernetes folks directly that are not necessarily using Cloud Foundry, they'd expect, for sure, higher level abstractions as custom resources. So my feelings tells me that you want to have a custom resource representing your service bindings and most importantly your service instances. And then your service broker can delegate the heavy lifting to those controllers behind those custom resources. And in the end, what you'll then do is translate that into lower level, more Kubernetes native resources. Well, nobody will hinder you to use higher level or external third-party things like a service mesh in a controller when creating service instances. So it's absolutely up to you. So the takeaway here would be Cloud Foundry, service brokers, that's the same. The responsibility of the service broker will change a bit. For example, because in case you delegate the heavy lifting of storing and reconciling resources such as the data service instances themselves to controllers running inside of Kubernetes, do you have to store much of state in the service broker anymore? Or could you run your service broker in Kubernetes and rely on its etcd for persistency? So the design of a service broker will change the way you express your and implement your service instances, and bindings will change using Kubernetes resources. But the tools are there, all you have to do is assemble it. So there's much to talk about left. For example, how do you package, ship, and run these operators? What about the weaker container isolation? Are there workarounds for that? What's with this additional effort? Logging, metrics, scaling, harmonized backup and restore. So if you want to talk, if you want me to talk about this, ask questions or leave comments if you're watching this as a recording. I'd be happy to produce more talk proposals in this area. All right, so summing it up, we need to keep an eye on the weaker container isolation, as this creates some challenges that can be mitigated but create additional overhead in the automation. For example, host affinity, anti-affinity, taints, and so on. Kubernetes can do data services. There are resources for that. There are stateful sets, services, config maps, and secrets. And there are also utilities emerging that will help you to deal with these things more gracefully, including the Operator SDK and Kudo. My personal belief is that there is still room for improvement because it's still a tedious task to describe a data service lifecycle. So watch out for new technologies to pop up. If you have questions and opinions, feel free to provide feedback and questions. And so far, thanks for your time. One advice: if you felt lost a bit because I threw around with a lot of Kubernetes terms that you are not familiar with, maybe you want to have a look at learn.kubernetes.anynines.com. It's a free Kubernetes tutorial. We use that internally to train up new engineers to do the basic Kubernetes and get through the Kubernetes basics. So maybe you want to have a look at it. There's this tutorial, and there's on our YouTube channel, the Anynines YouTube channel, there's also a 12-hour recording of a session where we go through this tutorial in depth. So have fun with it, and thank you very much for your attention. Reach out if you have questions. I'm on Twitter. Looking forward to talk to you. Bye-bye.